So welcome to the week 10 of the course. Up until now we have been seeing several new techniques in parameterized algorithms, and in this week we will learn another new techniques in parameterized algorithms called algorithms based on algebraic technique. And one of the first technique that I would like to talk about is what is called inclusion exclusion based algorithm. Okay. So now what is the principle of inclusion exclusion? Let's try to understand that. So the principle of inclusion exclusion, there are several formulations you have seen. We will see the more classical formulation later, but let me tell you something slightly different formulation, and maybe this will help you. So basically what we would like to show is that there are as many odd sized subsets as even sized subsets that are sandwiched, okay, sandwiched between two different sets. Okay. So what I mean by this, okay, so let's spell it out. What does it mean? So this basically means, so we'll prove this, for R subset of T, okay, for R subset of T, okay, look at R is there, S is there, okay, and I do -1, then this is equal to okay. So let me introduce this notion. This is also like this notion. Basically, what I mean, yeah, okay. So what is this notation means? R equal to 2. So this is basically what is called, we use what is called Everson notation, okay, Everson notation P for proposition P, okay, meaning this evaluates to 1 if P is true and 0 otherwise. Okay. So in the context of this, what does this mean? That this expression, the left hand expression, is equal to 1 if R and T are equal, otherwise 0 everywhere. Okay. Now look at this expression. What does this tells us? This expression tells us that you fix an R, you fix a set T, and you look at all the sets S which contains R, but it is contained inside T, and then you look at the -1 to the power their cardinality. So notice that all the odd sets here are going to contribute -1, and all the sets S which contains R and contain inside T and that are even are going to contribute 0, because they are going to contribute -1. So the odd sets are going to contribute +1, even sets are going to contribute -1. Okay, and if R and T are not equal, then the number of contributions that will come from all the odd size sets and even size sets, they will cancel out each other, and this is exactly what it means, that there are as many odd size subsets and even size subsets sandwiched between two different sets. Okay. Okay, so now let's try to prove this. Okay, this is not very difficult, so let's try to prove this. Okay, so let's try to prove this. Okay. So how are we going to prove? Let's take first R is equal to T. Then in this case, right, in this case there is exactly one sandwiched set, okay, sandwiched set, and what is that? Namely R equal to T, right, and then the left hand side, okay, sorry, okay, and in this case namely R equal to T, okay, and so the left hand side will become, there is only one contribution, that is minus 1 to the power 0, right, which is 1, and in the right hand side, what is that? In the right hand side, you know that R is equal to T, so this notation also evaluates to 1. So this is fine. So now let us assume that R is a proper subset of T. So now what are we going to show? Now to show this, we are going to, how do we prove this in this case? We are going to set up a bijection between odd and even sized subsets. Okay. So we are going to set up a bijection between odd and even sized subsets. Okay. Yes. Okay. And how do we set up such a bijection? That is very easy. You know that R is a proper subset of T. So let T be an element of T minus S. Okay. Let T be an element of, sorry, not S, but T minus R, okay, because you know. Now for every, so what is the bijection we are going to give? Okay, for every odd size subset S1, okay, so let us write it slightly better. Okay. So for every odd sized set, say S1, that contains S and contained inside R, okay, so T contained inside R, okay, we are going to set up S0 is equal to S1, okay. And what is this notation? This is basically notation for symmetric difference. Okay. So now notice, okay, okay. So every odd size subsets, okay. So now look at S1. What kind of set S1 can be? T could belong to S. If T belongs to S, then what is S0? S0 is S1. So what is symmetric difference? So symmetric difference means this and this, right? Now if T belongs to this, then what is S0? It is basically S1 minus T, okay? And then in this case, what is S0 is even, okay. Now look at S1. Now T does not belong to C, then S0 is what? It is S1 and union T, right? So since we started with S1 as odd and we have added a new element to this, right, this is still even. So notice that we have been, so at least the mapping from odd to even is fine. So every odd set is mapped to an even set. And why this is a bijection? Because you can recover, right, okay, okay. And so this is one thing. We also have to show that R is, we also have to show that the set R is contained inside this. So now we started, look at the first case, right? Look at the first case, right? S1, right? We deleted T, but where the element T was, right? Where the element T was in T did not belong to R, right? So what does it mean? So if you looked at an odd set, you deleted an element who did not belong to R. So this implies that even in this case, S0 contains R. And since this is anyway you are adding an extra element from a set. So, this in this case also we can show that S0 contains R. So, we have been able to show, sorry, not R, my bad, T. Yeah, T, we picked up T in, yeah, T minus R. Okay, so I made a mistake here. Yeah, I made a mistake here. This is why. Okay. Yeah. So, yeah, T does not belong to me. This implies that this is fine, this is fine, sorry. Okay. So, either way, so the basic fact of the matter is that we have been able to give a bijection from, or we are given a function that maps even sets, that maps odd sets containing R and contained in T to even sets that contains R and contained in T. Okay. 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 Fine. So, function is established. Okay. Now, why it is a bijective? That is, it is bijective because we can recover S1 from S0 as, again you can do the same thing. So, what is S0? It is nothing but S1 okay. So, this is what, so we can recover S1, so our object from, so you do this, okay. Okay. So, you can recover, so look, so it's like I can get S1 by again doing the symmetric difference between two with respect to the set T, right. So, this is why this establishes a bijection, okay. And once you have been able to show that in the second case the number of sandwich sets of even size and odd size are equal, right, when R is a proper set, then the left hand side contributions are like even number of plus ones and even like equal number of plus ones and equal number of minus ones. So, they will cancel out each other. So, left hand side is 0, and since R is not equal to T, so this right hand side notation will evaluate to 0. So, you are done. Okay. So, that is it. Okay. Okay. Now, so why did I tell you this? So, it is a very important and interesting algorithm we will make out of this. So, first example I would like to give is in graph coloring. Okay. Okay. So, what is graph coloring? Okay. So, graph coloring is nothing but it's a, so input is a graph G, integer k, and question is, does there exist an assignment from vertex set of G to an integer 1 to k, also called colors, okay? Okay. Such that for each edge UV assignment F, FU is not equal to FV. Okay. So, basically you have a graph and you want to assign numbers. So, for example, this is not a proper coloring because there is an edge here, and both endpoints have been assigned the same color. Okay. But This is a proper coloring, because look at any edge, the assignment maps different integers. Okay. So this is what is called K coloring of a graph, and the question is, does there exist such an assignment? Does there exist a coloring of vertices with colors 1 to K such that no edge is monochromatic, meaning that like same color is not assigned to the endpoint of any edge. Okay. All of you know that this problem is NP hard even for 3 coloring, meaning if you are looking for an assignment from color 1 to 3, even then the problem is known to be NP hard. So hence, expecting an algorithm of running time, say f of k n to the power big O of 1, or even an algorithm with running time some n to the power f of k is not possible, because if you could design such an algorithm, then what it will imply? Substitute k equal to 3, then what will you get? F of 3 n to the power big O of 1 or n to the power f of 3. Whatever it is, for value 3, this is either polynomial, both of them are polynomial time algorithm, right? So unless p equal to np, we do not expect that we will be able to design such an algorithm. Okay. So for this, we are going to use a parameter which is cardinality of v, g, at n. So we are going to use our parameter n, the number of vertices. Okay. Okay. Now, okay. So we can ask, is this k coloring problem, is this k coloring problem FPT parameterized by n? But now let's see how many number of assignments or coloring are there. How many assignments or number of colorings are there? Well, number of assignments or coloring are how much? So you are looking for a total number of functions from 1 to n to 1 to k. So every vertex could be assigned one of the k guys. So the number of such functions, number of f's are upper bounded by k power n. Okay. So you can enumerate each of these function and check whether they form a valid coloring or not. So the one trivial running time of an algorithm could be k to the power n and n to the power big O of 1. But now you know that, like, yeah, so this is one. So if you are looking for a proper coloring, and generally this is like you are, look, so for example, if k is greater than or equal to n, then you can trivially do this, assign every vertex different color, and you are done. So we can assume that k is less than or equal to n, okay, and hence n to the power n, n to the power big O of 1, right, which is 2 to the power big O of n log n, and we are happy. Okay. Okay. So now, as we have been trying to do, okay, so what is the goal? So goal is fixed. So the goal is to design an algorithm with running time c power n, okay, where c is a constant, okay, and where c is a constant, okay, and of course c as small as possible. Okay, so that is the goal in this area of computer science. Okay. So just to give you a motivation, let's start with 3 coloring. Okay. Okay. So, I want to assign from 1 to 3 and I want to do better than 3 to the power n, okay, because the trivial algorithm is 3 power n and the question is, can we do better than 3 power n? Okay. So, now let us look at a valid coloring. Okay. So, valid f is an assignment to 1 to 3. Okay. Now, notice f inverse of 1, right. Let us call this V1. So, let us call this, we will use Vi. So, now look at this graph. Okay. Now, all these vertices has been assigned 1, all these vertices has been assigned 2, this has been assigned 3. Now, notice that there are no edges here, right, because otherwise this will be monochromatic, right. So, basically what is the property? The property is that each Vi forms an independent set. Okay. Okay. So, that is one observation. Okay. And secondly, in fact, it is partitioning of vertex set G into k independent sets. Okay. So, we will come back to this principle in a minute. Okay. Okay. So, once you have seen this, there is a very simple algorithm for testing whether a graph is 3 colorable or not. How? So, the algorithm for 3 coloring is very simple. Okay. Here is an algorithm for 3 coloring. Okay. So, what is an algorithm for 3 coloring? First, enumerate an independent sets. Okay, right. Okay. Rather like, let us look. For all x subset of Vg, x being an independent set, check whether G minus x is a bipartite graph, right. Now, notice that if I have guessed the color class 1 correctly, then the graph induced on 2 and 3 is nothing but 2 colorable, or nothing but graph induced on color class V2 union V3 should form a bipartite graph. Okay. So, this is why I checked. So, notice, so this algorithm will run in time. The possibility of x, number of x's are upper bounded by 2 power n. Okay. So, 2 to the power n, n to the power 1. Okay. Okay. So, this is one algorithm and okay. But now you can ask yourself, what about forecoloring? Right. So, now you are looking for an assignment from Vg to 1, 2, 3, 4. So, now what I can do? Okay. Okay. So, now let us make an algorithm for forecoloring. X being an independent set, check whether G minus X can be 3 colored. Okay. So now we made changes here, right. So rather than checking whether, I said okay fine, now what is an algorithm for forecoloring? Algorithm for forecoloring is nothing but you, right. So once I have guessed V1, in the remaining V2, V3 and V4, the graph is 3 colorable. Okay. So in this case, now in the first case we had 2 power n and we could do this checking in poly time, but now we cannot do this. So, but for this we have an algorithm with running time 2 power n, right. So if you do naively it will become 2 power n times 2 power n 4 power n, but that's not how you should be doing, right. So basically you have to do in choose I going from 0 to n. So this is possibilities of x, okay. And then in the remaining, how many vertices are left? In the remaining, the total number of vertices are left is n minus I, and on that you run your 2 to the power n minus I algorithm. So this is going to be 3 to the power n, okay. So just generalizing this, you can get a k coloring algorithm in running time. But this tells us something, right? I mean, this tells us, this idea of an algorithm tells us something, that X being an independent set, whether check whether G minus X is 3 colorable. So once I know the first set, in the remaining I need to know the chromatic number of G minus X. Okay, so that just implies that this is like this immediately implies that maybe we should look for a dynamic programming algorithm, and in fact you can design a dynamic program, a simple dynamic programming algorithm based on the following recurrence. What is the following recurrence? Okay, so if you are looking for a k coloring or chromatic number, you can do anything. Okay, so look at A x. Okay, so what is A of x? It is going to write down the chromatic number of graph induced. So now let's try to compute chromatic number of G. Okay, and what is the chromatic number of G? Minimum number of colors required, minimum number of colors required, so that we have a valid coloring. Okay, so this is what chromatic number is, like minimum number of colors you need so that every edge can be non-monochromatic. So this is what A of x is going to, what is A of x is going to store? Chromatic number. So what is A of graph induced on? So I'm going to say look at A of x, look at it. So I guess the first independent set. Okay, so this is going to be minimum over y subset of x. Y is an independent set, that's the first thing. Okay, y is a subset of x, y is an independent set, and what is y? Y is an independent set and y is not equal to phi. Okay, fine. So you have guessed the first thing. So it is 1 plus the chromatic number, the minimum number of colors you need for the graph induced on G minus y. So this is A x minus y, and that's it, right? So I'm trying to have an array A of x. So basically A of x is indexed by A of x is indexed by indexed by subset of my vertex set. And what does A of x stores? A of x stores the chromatic number of that, and that can be given as minimize y subset of x. Y is an independent set, y is not equal to phi, and 1 plus this. Okay, so now so this is a big array. Okay, and you index them with subsets. Okay, and you fill this up in the increasing order of sets, and if you fill this up in the increasing order of sets, okay, increasing order of size of sets, sorry. So you first fill up the 0 size set, then 1 size sets, then 2 size sets, then 3 size, so on and so forth. And what is this? This is 0. A of phi is 0. Okay. And now to evaluate A of x, how much time will it take to evaluate A of x? Well, time to evaluate A of x is basically 2 power cardinality of x and table lookup, right? So you take you take 2 power x entries and you take minimum of that and you put that entry. Okay. So the running time of this algorithm is again going to be n choose I and 2 to the power n minus I. Okay. Yeah, because that is one, and this is going to be 3 to the power n. So you can compute chromatic number of a graph in time 3 to the power n. So there was lots of work happening in this area to get 3 power n to something smaller. Okay, something smaller. Okay, and with lot of effort, it was stuck at roughly, I would say, 2.4. Okay. This is not accurate, but this is 2.4, right? Roughly, it was stuck, and then there was a very beautiful algorithm which we are going to see now. Now, using inclusion exclusion, we will see 2 power n algorithm. Okay, okay. So that will be our goal, using inclusion and exclusion to see 2 power n algorithm. Okay, okay, okay. Okay. So now let's go back to our coloring perspective. Okay. So what is a coloring? So as I said, so like let's look at any color assignment. Okay. Coloring. Okay. So basically, as I said, it's a right. It's basically every valid coloring or every say proper coloring partitions V of g into k independent sets. That's very clear that every proper coloring partition Vg into k independent set. But what about the other way around? So if I have a partition of say V of g into k independent sets, what does that imply? Okay, so I have this is partition of Vg into k independent sets Vk. The moment I have a partition of Vg into k independent sets, I could assign color 1, 2, 3, k, and if you notice, because these are independent sets, there are no edges here, which implies that this is a proper k coloring. Okay. 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 So now what are we able to prove? We are able to prove that the following lemma, that G has k coloring if and only if V of G can be partitioned into V1, V2, Vk can be such that each Vi is an independent set. Okay, and that's perfectly fine. Okay, in fact, so this is, so we have reduced, what we have done is we have reduced k coloring to partitioning into k independent sets. Okay, and we will utilize this fact to do inclusion exclusion. Okay. But before that, let's make it even better. In fact, what we can say is the following. Okay. We can prove a better, slightly more general lemma, and we say a graph G is K colorable if and only if G can be covered by K independent sets. What is the meaning of this? Let's try to focus there. Can be covered with K. So basically, what I'm saying, a graph G is K colorable if and only if I can find V1, V2, Vk. Okay. Vi's are independent sets. Okay, and union of Vi, I going from 1 to k, is equal to Vj. Okay. I am not claiming that they should form partition. What is the meaning of partition? A vertex will not appear in two different sets, right? So, I am saying that, look, of course, K coloring is same as partitioning into K independent sets, but in fact, what I am saying that it is K colorable even if you could cover the all vertices with K independent sets. Okay. So, these are basically two differences. Okay. So, now let us prove. Forward direction is very easy. Forward direction is very easy. If a graph G is K colorable, then you know that they can be partitioned into K independent set, and hence they can also be covered into K independent sets. In fact, even better, no vertex appears twice. So, forward direction is very simple, but what about the backward direction? Now, we know that we have these sets, maybe like this, okay. V1, say V2, V3, V4. What is the property? Vi's are independent sets, okay, and union of Vi's, I going from 1 to k, is equal to Vj. Now, given this covering, we will from covering we will recover a partitioning. Okay. How? You fix V1. Okay. Okay. And now, what is V2? Okay. So, what is the new? So, V1 is V1. We will make a V2 prime, which is nothing but V2 minus V1. Okay. Okay. Fine. So, similarly, so basically when you are trying to construct Vi prime, it is nothing but Vi minus union of let us call this V1 prime is equal to V1 equal to I going from j going from 1 to I minus 1 Vi Vj, right. So, whatever previously you have selected, just remove all those vertices. So, Vj only contains those set of vertices which does not appears in V1, V2, Vi minus 1. Okay, that is it. So, now notice that because of this we have, and this is how you can get Vk. Now, notice that every vertex is in some set, okay, and in fact, every vertex is exactly in one set because we have made sure that no vertex appears in more than one set, and all of these are basically a subset of an independent set. So, they are also independent set. So, from giving a covering, we have been able to obtain a partitioning of independent set. So, what does this imply, right? So, now we have actually reduced our problem from, if you want to test whether graph is K colorable, we are asking can we cover the whole graph with K independent sets. Okay? So, that is it. So, we will use, so notice what does this implies? K colorable if and only if K independent set partitionable if and only if K independent set coverable. That is it, right. So, we will use this for our purpose. So the lemma which we would like to prove, okay, is the following. And we will see how we can use that to design our algorithm. Okay. So to do this, before this, let G of S denotes the number of non-empty, okay, non-empty independent sets, okay, in okay, non-independent sets in S subset of Vg. Okay. So basically, rather you should say that G of S is number of independent sets in graph induced on S, but non-empty one. Okay. So this is what G of S means. So for example, okay, so let's call this, okay. So this is one independent set of this graph, okay. All singletons are one independent set, and if you look at the two independent set, it can only be this and this, or it can be this and this, that's it. So but we are only talking about non-empty independent set, we are not talking about empty independent sets, okay. So now what we can say about this, okay, so the lemma is the following, okay, now that we have set up the notation. A graph G is K colorable if and only if, okay, summation S subset of N, okay, rather than say Vg, okay, let N equal to Vg, okay, just so that it's easier to use notation. Okay. S subset of N, sorry, minus 1 N minus cardinality of S okay. So remember, what is G of S? Okay, G of S is number of independent sets, non-empty independent sets in my graph. And why we are talking about non-empty independent sets? Because you want V1, V2, V3, each of them to be non-independent. Okay. So now to prove this, okay, we'll prove this. Okay. So what is this G of S K counts? So basically notice what G of S K counts is basically it counts you number of ways to pick K independent sets, right? So I'm not saying that like, look, number of ways. So now we'll do a proof for this. Okay. So to prove this, okay, first what does it tells us that look, what is G of S to the power K? G of S to the power K is number of ways to pick K independent sets. So our intuition is that, so in particular, what is a good way of picking K independent sets for our purposes? If for us good will mean, okay, so let's try to understand what is G of S to the power K means. Okay, it counts the number of ways to pick K independent sets. Okay, but let's say if I selected some K independent sets, I selected some K independent sets. Okay, and suppose S equal to n, which is equal to vertex set of G. Okay. When some k independent sets will be great for us, because if you picked up k independent sets, say I1, I2, Ik, and if their union is equal to V of G, great for us, because once it means I have picked up k independent set that can cover whole vertex set, because then covering implies partitioning, implies coloring. Okay. So this is great. But when is not this great? If union of EI is a proper subset of EJ, because their union can only be, right. So if I look at the whole vertex set and like for S equal to n, let's pick up k independent sets. Okay. These independent sets are great if I have picked up k independent set which can cover the whole my vertex set, but it is not good for me if it is proper subset. Okay, fine. So now what basically I will tell you that, look, in this expression, only thing which will matter is those counting for which, like, so the only those ways of selecting k independent set will contribute which equal to Vg, and rest rest of them are counted equal number of times with -1, equal number of times with +1, and hence they will cancel out each other. So that is the goal of doing this. Okay. So now let's try to express left hand side slightly better, slightly differently rather. Okay. So what I can say, so what is this? Summation -1 n minus cardinality of S. Okay. G of S to the power k. What is G of S to the power k? It is some number, right? So some number to the power k is nothing but some number times some number times some number times some number, right? And that number is nothing but summation of 1 plus 1 plus 1 plus 1 plus 1. So we can write this left hand side is equal to summation S going from S summation I selected an independent set I dot summation I selected k independent set, right? And what is the property? That for all I, this is your that notation, for all I belongs to set S and -1 n minus S. That is exactly the same thing. Okay, that's it. So like what does this mean? Look at all the independents. So suppose like among all the independent sets of my graph, look at those who belongs to S. So you are summing over those, right? So what is this left hand side? So it is nothing but G of S -1 to the power n minus S into G of S. Okay, fine. And what is this summation? Again you are going over the same thing. So it is -1 G of S to the power square. So if you do k times, you will get summation over S, this. Okay. Now, but I could also do this slightly differently, right? I could go over all independent sets of my graph, k independent sets of graph, and only count this when each of these I1 to Ik belongs to S. So what I mean by this, so this is, I could write this summation I1 dot summation Ik. So where these IIs are independent sets in graph G. Okay. Okay. So I am going to do summation over k independent sets, but they should only contribute when. But now, so I first collected k independent sets, and now I am going to sum. This is important point. I am going to sum over S. Okay. Okay. And now, so I took up k independent sets. Now these k independent sets could, like this k independent set could be contributing to several S. Okay. So this is summation, okay, for all I is a subset of S -1 n minus S. Okay. Now if you picked up k independent set, now you ask yourself, if you have picked up k independent set, how many S will you contribute to? You will contribute to those S's for which I1 to Ik is subset of S. Okay. So we can write down, okay. So this could be again written as Ik, okay, and summation over, okay, so this is going to contribute to all, because look, I1 is also part of S, I2 is also part of S, Ik is also part of S, okay. So this is only going to contribute to those sets S, right, for which their union is contained inside this, okay. And then this is it. Now look at this inner sum, okay. So now let's look at fix some I1 and Ik. Let's fix this I1 to Ik. Let's call this set their fix some k sets. Okay, let's fix I1 to Ik, some k independences. Now let's call R equal to Ik. So this is my R, okay, and my T is vertex set of G. Okay. So notice that these k independent sets are going to contribute when these k independent sets are going to contribute when these k independence, this I1 to AK are going to contribute for all S which contains R and which is properly contained inside T. Okay. Fine. So this is where it. Now we know that this. So you fix I1 to Ik. Then once you have fixed I1 to Ik, then their summation is for all S that contains this. So the innermost sum, this innermost sum contributes only when, okay, contributes when, only when R is equal to Vg, right? So for all, so now what we have learned? We have learned that, look at this, look at this inner sum. Now any covering of k independent sets that is not equal to vertex set of G, that is counted equal number of times with negative sign and equal number of sign with positive sign, and hence that guy contributes 0. So the only people who contributes here are those, only people who contributes here are precisely those, okay. So only thing which contributes are the covering of, like only things which contribute to this like non-zero way or yes, is when I have I1 to Ik which covers the whole vertex set. So what we know? So if, okay, so we have learned that if, right, if summation S subset of n minus 1 n minus s g of s k is greater than 0 implies we can cover vertex set of G into like this is greater than 0 if and only if, not rather we should not say that, okay. We can cover Vg into Vg, we can cover Vg by k independence, not into k independent set, by k independent sets. Great, okay. And now we know that if we can cover Vg by k independent set implies G is k colorable. Okay. For the reverse direction is very simple. If G is k colorable, implies we can cover Vg by k independent set. If we can cover Vg by k independent set, then this sum is always going to be non-zero. In fact, when we have G is K colorable, then we can cover V of G by K independent set which are disjoint partition. Okay, great. So we have been able to show that if a graph is K colorable, if and only if following combinatorial identity is true. Now let's try to see how we can use it, this combinatorial identity algorithmically. Okay. Now let's try to, so what we would like to do? We would like to compute this quantity. What is this computing this? So basically what this quantity computes, let's first write it down. It computes for all S subset of N, which is vertex set of G, number of independent sets, right? What is its count? So it basically takes number of independent sets of graph induced on S. Fine. I mean, like, and then, so we can do this very easily, right? You look at graph induced. Try all subsets S prime subset of S and check if S prime is an independent set. Okay. So you look at all non-trivial independent sets S prime subset of S and check how many of them turn out to be a independent set. So this can be done in time 2 to the power S time. Right. So in 2 power S time we can compute G of S and take its kth power and look at this summation. So we can evaluate this summation in time. Summation again we can do the same trick, n choose I going from 0 to n, 2 power I, and that is like 3 to the power n. Okay. Okay, so this is, so we didn't get anything new when we try this inclusion exclusion formula than what we already knew before. Okay, because of this, but notice that this algorithm is a polynomial space algorithm, right? Because all we need at any point of time is like you go through S one by one, right, and keep a sum of what is the current evaluation is. So that's like one memory, and for you look at the current graph, current S, and you enumerate all subsets one by one. Again you have a counter, and that is how you can compute G of S in poly space. So in fact, so what we gave before is 3 power n algorithm, but with 2 power n space. So what did we give before? So we gave 3 power n algorithm with 2 power n space. Now we have given another 3 power n algorithm, but with polynomial space. Okay. Now what I am going to tell you is that actually we can do this computation much more easily. So rather than doing this, what we will do is that we are going to, before even running this algorithm, we will build a table, okay, with 2 power n entries containing G of S for all S subset of n which is equal to V of G. Okay. Okay, and to do this such a thing, I can build a recurrence, right? And how will I build a recurrence? First of all, notice that G of empty is 0. Now look at some S, okay, and fix some V in S. Okay, so now independent sets in graph induced on S are of two types. One, those who does not contain V, and those who contain V. Okay. Those who do not contain V are same as those which are independent set in graph S minus V, which you have stored, this is same as G you have stored here. Now, if you contain V, then there are, so if you contain V, then first of all, V itself could act as an independent set, or you have to find an independent set. If you contain V, then none of the closed neighborhood of V can be contained, right? Because V, right? If V is there, none of its closed neighborhoods are there, which implies that in this case you are looking for, okay, you compute the independent set in graph G S n minus V, okay, add V to that, so that is one family of independent sets, plus you have to also add 1 for V itself. So, this is nothing but G of S minus NV plus 1. So, that implies, that immediately gives us a recurrence. G of S is nothing but G of S minus V plus G of S minus N of V plus 1. Okay. So, this belongs to V in S. Okay. Okay. Okay, that's it. So, once I have this recurrence, then I can again fill this table, okay, in, so first increasing order like phi, then all 1 length sets, 2 sized sets, okay, and at any point of time you are looking, you just need 2 entries from your array which you have already pre-computed. So, each index can be computed. So, you like, so these sets, these are indexed by a sets of your vertex set, and to compute each index set you only need to look at 2 previous entries. So, you can fill this up. So, you can fill this up, fill this table in 2 power n to the power big of 1 time. And now, once you have computed this, okay, right, now you have computed this, oh sorry, okay. Now that you have computed this table G of S, now you go one by one and like you evaluate these numbers and just check this. So, now with the help of the table, we can compute, with the help of this table we can compute the sum in 2 power n to the power big of 1 time and 2 power n space, okay, 2 power n time and 2 power n space, okay, and based on the number we know whether G is K colorable or not. Okay. So, in terms of time, this is the state of the art. Okay. So, in the next lecture we will continue our foray in inclusion exclusion, but this time I will give you the classical, that intersection way or union way of doing the inclusion exclusion, and then we will take it from there and give another example of inclusion exclusion, and then we will move to the different techniques in designing algebraic algorithms